Welcome back. In the previous session, we learned about the basic concepts of the genetic algorithm. And in this session, what we will learn is about crossover and mutation operators. Okay, so for crossover operator, assume that we have chromosomes in binary format. For example, P1 is a chromosome and it is given by these binary numbers, actually the set of binary numbers. So as you can see, we have 8 binary numbers, actually just zeros and ones, and they are as our first parents. Okay, well, we can show this as a graphical shape. As you can see here, actually we are going to use a binary cells, and we are going to fill the cells corresponding to values of ones. So far we have the first parent, and let's assume that we have another parent here, actually 1 1 1 0 0 1 and 0, and I showed this as a graphical shape. As you can see, we have ones here and another one here, and so this is a graphical representation of our chromosomes. And if we are going to combine the information of these two parents, we can do this in several ways or using several operators. In this slide, I just closed the graphical shapes to each other. So for example, we can cut these from this place and then switch these parts, this known as, as single point crossover. We are going to randomly select the position for cutting both of chromosomes and then switching one part. For example, the right hand side part, okay? And this results in 2 new chromosomes. We can simply display them as these, and they remain same. So we have these parts, but the right hand side parts are switched. So we have just one here, and we have one here, and 2 ones here, and these are offsprings. Okay, these are actually parents, and this is offspring 1 and the next one is offspring 2, and they inherited some of characteristics from first parent and some of them from the second parent, and so we have 2 offsprings. And hopefully, for example, if the answer is all zeros, then offspring 1 will perform better, actually will outperform its parents and the other offsprings, its sibling actually. So hopefully crossover will improve our solutions, and if we perform this crossover operation in several generations, then we will have better and better solutions. And in some iteration or in some generation, we will probably find the solutions, actually the optimal solution of the problem. So this is the simplest crossover operator, actually single point operator, but we can do another type of crossover. Okay, so for example, 2-point or double point crossover, which has 2 cutting points, and for example we select these 2 cutting points and we switch the middle part here to get new offsprings. Okay, so what you can see here is double point crossover, and if we do so, we will get 2 offsprings in this form. So these parts and these parts remain same. Okay, so we have here, and we have this here and here. So we are going to change these middle parts. So we have this here, and this is the offspring 1. So the next one is offspring 2. So these are the offsprings created by double point crossover. Okay, remember that these cutting points are defined randomly, and it makes possible to create a set of possible offsprings, which is a randomized operations. So after all, this is another crossover operator, and we have another one, but here we are going to say that which one of genes are inherited, for example, from first parent, and which one of them are inherited from the second parent. Okay, here I'm going to say that, for example, for the first offspring, these genes are inherited from the first parent, actually these 5 genes, and the other ones are inherited from the second parent. We can model these as zeros and ones, And you can write instead as these marks, actually 1 0 1 1 0 1 1 0, and you can numerically multiply this element wise by this and its complement by this to get the offsprings. Okay, so as you can see, we have the complement of these values. So we have cross here and cross here. Actually, these are complements of these check marks, and we have check marks here. So its numerical equivalent is 0 1 0 0 1 0 0 and 1. So we can multiply this sequence by first parent element wise, and then we can find the value of first offspring. And this converts to process of generating new offsprings to an arithmetic to a mathematical operation. So this is called uniform crossover. And if you're going to find the value of offsprings, we can calculate these in this way. For example, 1 times 0 plus 0 times 1 equals to 0. And it can be found directly from this. And we inherit this gene from the first parent for this offspring. You know, for the first offspring actually. So this part is 0. And 1 times 1 goes to 1. So we fill this. And so on. So we use these sequences. So empty will remain empty and empty will remain empty. We use this empty, so it remains empty, and we use these, and finally that's it. So if you calculate all of these, or if you gather these 5 genes from the first parent in these 3 genes from second parent, you will get this. And for creating the second offspring, we do this in reverse direction, actually with reversed values for these flags. And then, for example, for this gene, it must inherit from the second parent. Okay, so it will be this, and it will be 1, it will be 1 here, and it will be empty, it will be 1 here, and it will be empty, and it will be 1 here, and it will be 1 as well. So we have these offsprings as outputs of uniform crossover. And if we want to write it as mathematical operations, assume that we have first parent. For example, as the first parent, we have x1 equals to x11, x12, x13, up to x1n. And for the second parents as well, we have x2 equals to x21, x22, up to x2n. And we are going to calculate these values for offsprings, actually y1 and y2. And so we have these offsprings, actually, as I mentioned earlier, y1 and y2. So x1 and x2 are our parents, and y1 and y2 are the offsprings. So for calculating these values, we must create some flex. For example, a vector of binary numbers, zeros and ones, which named alpha. And for these, we have alpha 1, alpha 2, up to alpha n. And then we will have the value of 2 offsprings as this. y1i will be equal to alpha I times x1i plus 1 minus alpha I times x2i. And that's, if alpha I equals to 1, then y1i will be equal to x1i. So the first offspring will inherit the gene, and if alpha equals to 0, then this term will be 0, and this term, actually 1 minus alpha, will be 1. And so if alpha I equals to 0, then the first offspring will inherit from second parent. After that, we calculate y2i by this, actually 1 minus alpha I times x1i plus alpha I times x2i. And you see that this is the mathematical formula for uniform crossover. So we reviewed 3 types of crossover operators, actually single point, double point, and finally uniform crossover. And the uniform crossover can be represented by these equations as well. The next operator which I'm going to talk about is mutation. In the nature, mutation is a kind of error in replicating and copying genes, and we included this mechanism and simulated inside genetic algorithm to add some levels of errors which increase the explorative abilities of genetic algorithm. Actually, it makes possible to create innovative and revolutionary solutions for our problem. So that's a good idea to have a simulated mutation process. So to do this, we have an operation which accepts a single solution and it returns a mutated version of that solution, actually a mutant. And it works in this way. For example, for the binary representation. From now on, I'm going to talk about the binary representation, and later we will discuss about the mutation in continuous or real variables space, okay? For example, assume that we have this solution, actually this chromosome of binary genes, actually x1, x2 up to xn, and we know that all of these are either 0 or 1. So firstly, we will select and index j randomly from 1 to up to n. So j is a random number actually in this range, okay? And after selecting an index, we are going to alter xj using this set of equations. We have x prime as this, actually x prime 1, x prime 2 up to x prime n. And we have x prime I, generally equal to xi for i's that are not equal to j. And if I is equal to j, then we must replace this value with a different value. And we know that we have 0, either 1 as possible value. So we are going to use this equation, actually this expression, which changes zeros to ones and ones to zeros. So if xi is 0, then x prime I will be 1. And if xi is 1, then x prime I will be 0. So this changes the value of x prime I, and this is a simple process. Actually, this is a simple mutation for binary representation, and we can use this. However, you can select more than one index, and you can select multiply indices to perform this kind of change in binary representation if you want. And that is defined by mutation rate, and that's selecting, for example, 2 genes out of 100 genes is equivalent to a mutation rate of 2%. And if you want, you can increase the level of mutation or the mutation rate, and that's up to you. However, for different kind of problems and different kind of search spaces, we will use different mutation rates. And that parameter should be set according to the conditions of problem and search space, okay? So we have this operation here, and we know that after crossing over, we have some offsprings, and we are going to mutate those offsprings to get mutated or mutant offsprings. So this is the end of reproduction phase here, step 2 and step 3. Then we are going to talk about the selection operator here and here, which are different from each other. Actually, despite the fact represented by the same word, they are different in nature. But the selection operators will be taught in the next session. Many thanks for watching. Don't forget to hit the subscribe button and bell icon to receive more videos every week.